Okay, good afternoon, I'm Nordita, and I actually, well, this is what I've been doing for the past 14 months. I've been working with the pencil code using just the ready-made sample MRI turbulence hyper, and I actually haven't been touching the code, just modifying the input parameters, so I'm just, I know, getting there. The background that I have with the pencil code is that I completed my master's thesis last year, and my topic was the magnetic rotational instability in shearing box simulations, where I measured the Reynolds and Maxwell stresses and the Shapiro-Sunyaev alpha viscosity. And out of this came a follow-up paper, which is still unfinished, where we actually, in this paper, there are, in addition to me, there's Marek Korpi, Petri Käpylä, Vladimir Lera, and Axel. So we've been working on some new closure, but anyway, closure models for more accurate turbulence prediction as opposed to the old alpha parameterization. And this is what I'm about to, extrapolate on these results a bit. The things that these two studies had in common, they were both parameter studies, where we studied the turbulence stresses, or wished to study all the turbulence stresses in all of the MRI unstable regime, with this shear parameter ranging from 0 to 2, where the Q sort of characterizes the rotation profile. But in reality, we only got us down as 0.4, because when you got that low, you, no matter what you did to the hyperviscosities, you just couldn't get it, the Reynolds stress was most of the time below 0, no matter what we did. So I don't know, maybe we should have used, I don't know, larger groups or something. But anyway, this is our range. And the same sample was used in both studies, although we removed the dust that is in the sample. We studied an isothermal situation. There was no stratification. We had uniform density, and we used hyperviscosities to be able to use smaller grids to resolve the turbulence. So very, basic stuff. And the equations that had to be solved here were, non-ideal MHD equations. Here we use this operator that it includes the shear flow that you can see. Here is this nasty looking term that incorporates the shear flow, and we use the diffusitives here.
There should be a Euler gradient actually in the momentum equation, and still.
Sorry.
There should be still a Euler gradient term, if that's how you write it, in the momentum equation.
And there's a diff A term as well.
No, that's okay, because she has a row underneath the.
What?
The momentum equation, continuity equation is
Oh, my grab diff A should be, but that's not bad because she uses hyperviscosity. Usually there's a grab diff A.
Oh. Not in the.
That's the question of the
gauge.
Oh, yeah.
It has uniform, right?
Yeah. But I guess derivative there is really just a partial one for the electric equation.
Yes, right. They are all partials. No, actually that's correct, because she has she has this extra Q omega naught term in that. It's a special gauge. She is.
Right. So in our model, we set the size as 2 pi to 3. Resolution was 64 cubed, even 32 would have been enough, but it was slightly crummy. If you raise the resolution to 128 cubed, doesn't really bring anything, it doesn't improve the results all that much. We made these use dimensionless parameters, set all of these as one. We as I mentioned, was isothermal. And our magnetic field configuration looked like this, and we always set the amplitude to be the same as the angular velocity. And we use some Gaussian noise, the amplitude, so that in effect we always set this wave number to be 1, and because of this amplitude, the alpha velocity was always the same as the angular velocity, so this the maximum wavelength, or the most unstable mode of the MRI, was always well resolved because of this size 2 pi. So we took care of that. Now, because, well, apparently many of you already know quite a few things about the MRI, but some don't, so I'm going to go through this, introducing the Reynolds and Maxwell stresses, which I have called here the work causes of MRI. Magnetic stress tensor, actually, I haven't written anything in tensor form, but anyway. It couples to shear, which promotes turbulence. A Reynolds stress couples to vorticity, which suppresses the turbulence. So you see that when Q is very small, so are the stresses. But because this here is 2 times omega, so this vorticity keeps the Reynolds stress at a minimum. But when Q grows, vorticity eventually disappears when Q is 2, and then this turbulence runs away. This is what we call the Rayleigh unstable situation. So we can write down the radial total stress component to be like, well, R plus M, because M is negative. And this characterizes the turbulence strength. And the angular momentum transport efficiency results from these stresses. So this is where we stand. And this is, just to, show you a very, basic turbulent flow. We have these actually the what do you call it? Rotations. Orbits, thank you. And kinetic and magnetic energies, you can't actually see here this sort of a linear regime where this turbulence, the energies grows to this maximum, and then we reach a non-linear regime where we have sort of so-called saturated turbulence. So, as I mentioned in my master's thesis, we toyed with this Shakura-Sunyaev alpha viscosity a bit. Where do I write all these equations down here? You can write the alpha. This is the traditional way of writing it down. You have turbulent viscosity, which at the time of when Shakura and Sunyaev invented this, it was in 1973, and then the actual nature of MHD turbulence was unknown, but we needed some agreement on what to use if we want to study these disks. protoplanetary disks, for example. So it was agreed that the alpha viscosity is directly proportional to the pressure. And in our simulation, when we had placed the sound speed and the scale height of the disk.
So that you mean dxy divided by 2, I guess.
That's actually.
Oh,
Must
well,
be a-
yes, but going to be back to length scale. So maybe it's just the half.
No, I don't think so.
Well,
Alpha
what's
is
the question?
dimensionless.
No.
Well, okay, what do you mean? Well, it's not dimensionless? Oh, the last row you mean? No, that's okay.
Alpha should be dxy divided by the pressure problem.
Yes, correct. There's a division. The alpha is equal to dx divided by p.
Is it? Sorry. Okay, I've
Not
had
yeah.
my source.
But then there would be another factor of only unity also, actually a factor of 2.
But that's not really, what I mean. What I meant to demonstrate was that it is a very, very crude way of treating the turbulence. When, in our simulations, we set these as to unity, so alpha equals basically the turbulent viscosity. So we can write the kinetic and magnetic components of the alpha parameter like this. And some very, very early results. Back then we only got down to 0.6. I reran some of the simulations and got down to.
Is that because the growth rate of the MRI is so low when Q gets lower?
I'm sorry.
Is that because the growth rate of the MRI is so low that the viscosity comes in?
The problem is that the vorticity is, or this is what I've understood, the vorticity is so strong, it suppresses Reynolds stress. So it's so low, and at the same time there are fluctuations there, so you can't really get the mean there out.
But did you see an initial rise of the energy
Yes,
and then a decay?
yes. But the data, we couldn't get clean data.
So you saw the MRI, but you didn't see any saturated turbulence.
I mean, these are simulations without net flux, right?
Yes.
And so, in order to get this keep going, you have to make sure that it's not a linear instability anymore, of course. It's not linear from the very start.
What do you mean it's not
There's no application point for infinitesimally small perturbations.
But I thought, from the beginning you put in a fairly large scale magnetic field. I always thought that it was the linear stability just happening on some top of the magnetic field wave.
So, I mean, you have to rely
And
on...
that's what you call a non-linear, okay.
That's certainly right, yeah.
Yeah,
So you have to rely on the double positive feedback to be sufficiently strong, so that the turbulence is strong enough through the MRI, and secondly the dynamo is strong enough to make the turbulence again strong.
So effectively, this isn't a very exciting result. It only shows that the magnetic component of alpha dominates the accretion, and both components get really high, close to the Rayleigh unstable limit.
And the ratio stays approximately constant. The ratio between alpha and alpha.
I considered it's not the same, I think. No, it doesn't, because actually I've got some more data about it later on, because in this we said that the turbulence viscosity, the kinetic and magnetic components are effectively these. and I've measured the stress ratios later on, and they clearly show that the magnetic, the Maxwell stress dominates the Reynolds stress at the low Qs, but they reach, the ratio goes close to units here.
You mean when you go over 2 voltage 2?
Yes.
Okay. Cool.
So it can be even 100, the low end.
That's it.
But I'll get better pictures later on here. So there's obviously some need for a better viscosity model. Or not viscosity model, but the way to bridge the gap between theory and observations. Now, this alpha parameterization was useful when there still was no good theory of the MHD turbulence, and now there is the MRI. In alpha, we only consider these XY components. But actually in MRI, the XX and YY components of the rate of change tensor dominate the XY component. So they should be included. And recently there have been 2 papers by Ogilvy and Pessa et al. And they tackle this problem with more physically motivated closure models that are local. So we could use our already existing data to test these models. Why do we need closures? Well, that's basically because we don't have a complete theory of the MHD turbulence. You cannot analytically solve the properties of turbulence from the first principles. So in these closure models, they calculate analytically what they can, and the ugly, difficult, non-linear terms are enclosed in closure parameters that are positive and dimensionless. No, I'm not going to go too deep into these models because they are somewhat complex, and it's not really the point here because this is a principal code meeting. In Ogilvy's model, these closure parameters are solved from the components of Maxwell and Reynolds stress tensors. There are 5 parameters, that's what they stand for. It's not really important at this phase. And this is what these equations look like. These are covariant evolutionary equations that govern the dynamics of the stresses. So all you have to do is solve these parameters out of this. Now, from our simulations, we can print out all these X, Y, Y, Z, Z components and the X, Y components. These R and M here are traces of Reynolds and Maxwell tensors that can also be calculated from the simulations. Now this other, should have been 2006 in the previous slide as well. Anyway, it's a slightly different model, a bit, they try to predict the properties of saturated turbulence from the properties in the linear regime, which is quite remarkable because it goes against what I just said. There is no way to analytically solve these, solve the properties of the saturated turbulence from the first principles. They incorporate a new tensor W, which has all the current and velocity fields and their correlations in the linear regime. their evolutionary equations look like this. I'm sure you can't see anything. Be thankful for that. They basically look a lot, fairly similar to those of Ogilvy. We have zeta, a parameter called zeta here, and I'll show you where it comes from. It's one of the these are model parameters. Zeta is derived from the average wave numbers during the late non-saturated phase. So when we have turbulent energy growing and then it goes on. We're somewhere around here, I think. They are very non-specific about this in the paper. That's frustrating. And the other parameter can be solved when you have measured this data, and you have an equation for the growth rate of the stresses, and K max here is the wave number at which the turbulence has its maximal growth, experiences maximal growth. So here is the trace of the Maxwell stress. We can also calculate that, so we need this M0. And this is an energy density. And if you know all these from the simulations, you can solve this psi parameter. These are the closure parameters of Tesla, I thought. So what did we do? Oh, not yet. These authors use sort of standard parameters in their papers. Ogilvy ran his tests using setting all these parameters to unity, saying that it doesn't really matter if the model produces turbulence, no matter what positive parameters you use. Whereas Pesaro, they calibrated their model using an old data set by Hawley et al., a Keplerian set, and based on these old data, they give model constants for all Q, these values. And our aim was to see whether these constants were constants at all when Q was varied, and to see how well they predicted our shearing box data. So, to do this, we had measured stress components in our simulations that we put in the evolutionary equations that I just showed you, and solved the parameters from them for each value of Q. And then Petri wrote us a nice ideal routine, rerunning sort of these simulations using these fitted closure parameters to see whether they whether we get the same kind of turbulence that we had already measured. So here's what we got. These are very small, sorry. Here we have a total local stress. So these are the Maxwell and Reynolds stresses summed up. This dotted line here is what Ogilvy tells us that should happen if we set all the C1 to C5 as unity. And this line here is actually the output parameter. Yeah, the tendency is okay, but it doesn't really perform all as well. And our simulations but they're pretty much there. Not too far off. And Pessar does pretty well as well, even slightly better. Then with the fitted parameters, the accuracy doesn't really improve. And here are some terrible error bars. These are the stress ratios. Here we got as low as 0.4. And you can see this is the tendency that they show. The stress ratio is quite large for the small q's. And but the fact remains that these well, when you use these standard parameters, the at least for the Ogilvy model, it's it's a fairly good fit. Pessar doesn't do this quite as well, but it does when we have fitted the parameters, whereas Ogilvy fails here. And we did a small global experiment with the help of Vladimir. It was these closure models were local, but we wanted to see how they performed with global data. So these data points are from simulations run by Vladimir with varying Q, a slightly fewer data points because it takes a long time to run a global model. And the stress ratios are okay. They're actually fairly good. But at least for the standard parameters, the fitted parameters aren't as good for Ogilvy as others.
But is this also zero net flux?
I'm sorry.
Is this
No,
also
it's not. It's
but it should be zero net flux in order to compare.
Well,
I thought the analytics that assumed that you didn't have any net flux, or that doesn't matter.
The closure model was for zero flux, I believe. At least
Yes, what about the Pessar model? I mean, the Pessar model is based on the linear instability, but the linear instability you can really only have if you have a net flux, right?
they do actually assume that you have some mean flux or some net flux. I mean, on the equations you have this B0, and this is
Yes.
But what do they assume? What type of feature do they assume?
net field. It's a net vertical field.
I mean, I think
But
it's maximum growth rate, right? The beta is constrained by the constraint that the growth rate should be maximum. Is that right?
Yes. Yes.
But the growth rate is different.
The growth rate, of course, can be maximized for the suitable field strength. And that's the one they take. Is that one? I mean,
Yeah, they concentrate on the maximum growth rate because they assume that the other ones would be so small that they don't fit it.
Yeah, that's the probability you have to choose. But has that got something to do with the strength of the field? And that tells you which wavelength to focus on. Yes, does that depend on the strength of the field? I thought it was just some constant factor times the learn of it. I don't think it depends on the B0. I think B0 just sets the length gain of the MRI. B0 being the mean.
yes, the growth rate is maximized for,
Also length gain.
yes, that's fine.
But not for certain magnetic field. That only depends on the Cabrera omega and Q presumably.
Wait a minute, the maximum growth rate is for K times VA of your round 1, right?
Yeah, but
Right, yeah, that's right.
what is the
right.
maximum growth rate? That doesn't depend on the VA.
Oh, that's the
Oh, right.
3/4 of omega. of
Yeah,
course.
and it doesn't matter what B0
That's right,
is.
yes, yes.
Um,
So then, yes, sorry, yes, correct. So then the B0, of course, enters as a parameter, right?
only for the length scale. It depends on whether the length scale matters, and then you can probably say, well, we just choose a B0 where one scale height is the typical, is the fastest growing length scale or something. Probably not a crucial parameter.
Look that up again.
These are the stress ratios and the total stresses. Once again. Oh, sorry, this is still the stress ratio. Don't really, fit these models at all, which is, I suppose, to be expected. The interesting thing is that the stress ratio was fairly well predicted by these models, even for the global data. That's fairly interesting. But anyway, this paper isn't finished yet, but I think at the moment the consensus is that finding the fitted parameters doesn't really pay all that much. The accuracy doesn't improve much at all. So it's just a triple plus.
But here last results show that he has higher stress than the analytical model would predict.
Yes.
Right? I mean, that sounds like it has something to do with the approach field.
It could be that.
I think that's the most
That's
likely
what-
thing, that some approach field was not as true as the
Yeah.
analytical. I mean,
No, it's
you can also impose a field in the shear box, of course.
Yes,
So,
and we actually tried that. There was some problems with that. I think there was it just code crashed very
because
rapidly.
you start getting high marks on the
Yeah.
naming shocks.
Yes.
So I can also give you some parameters, some setup. I'm at a 0 on so pizza 400 or something.
That would be nice.
Another value of 0.5.
Yeah. Yes.
So 0.5, that's a lot.
You can, I mean, if your mean
This is hyper or hyper-viscosity and hyper.
it fits quite well with the first pseudocode measurement also, where they had a pizza of 400, which is in MRI connected a pretty strong impulse field.
Now that we are talking about MRI, and Toby is here, I mean, do you know what's the situation with imposed magnetic fields and the convergence?
No.
Has this been checked?
Yes, it has been checked by Pesa, I believe, in another paper.
The convergence.
Convergence with an imposed field. It's only the zero net flux that doesn't converge.
There's a technical difficulty apparently. I mean, and that's the reason why Sebastian von Rhein doesn't do it, because Zeus has problems with flux conservation in shearing boxes. And these, if you run for 100 orbits, that actually becomes very significant apparently. And so there are technical reasons why they haven't done it yet.
They don't say that in their papers.
But
They don't say that in their papers.
well,
Conclusion is both models work fairly well. There's one problem that I had last summer when I was still very fresh, young, doing this, even more so than now, and I was still learning to use the code, and I couldn't always remember how I had, distributed the processes. So this is what I expected to see. This run with 4 processors, with 2 processors in Y and Z direction, and 1 in X, of course. Then I made a mistake and got something like this. I was like, whoops, that looks wrong. And then I got curious, so I put the 4 processors to Y direction, and got this. And we reported this to Axel a year ago. I don't know whether this has been confirmed
I think you forgot. It should have been in the Baxilla, of course.
Yeah, but when you're young and experienced, you don't want to report anything formally, so I just
Shocked that I
yeah.
hear it here again.
Yes, what comes to haunt you?
This is a random initial condition or at least some random component in the initial condition?
There's the Gaussian noise. And it's similar in every other respect except for these processes.
It's strange. I mean, I always get the same values. You know, I have many resolutions and many different processes. I never tried that actually.
Yeah. It's interesting, really interesting to know whether this is just, you know, there's a machine dependent thing. But these will all run the same machine, and this is what I got. It's kind of curious. I thought maybe you'd like to know.
And that run is checked in? Otherwise you can,
Yes, yes. They are in Marit's.
you need to know the name.
I can't remember. I can
Yes, okay, good.
make them public.
Yes.
And maybe the most interesting part of this talk are my future plans with pencil code, when I'm actually going to get my damn hands dirty. What I'd like to do is to construct a collapsing magnetized cloud or a globule model to study star formation, and especially I'm not all that much interested in the star, just curious about the disk. What happens when we vary the rotation speed of the cloud and the rotation axis direction in relation to the magnetic field? Magnetic field strength, do we get ambipolar diffusion? Should we use what kind of ionization fractions are we going to use? And then hopefully get some observation time to be able to apply the model for some actual observations, and construct temperature, velocity, density maps from this sample, and the magnetic field configuration. We have a Monte Carlo based MHD code that's being developed in Helsinki, and we're hoping to construct some some spectra, what this kind of object would look like, to compare that to the observations. This kind of the modeling part has already been done, something similar by Matsumoto and Tomisaka in 2006. It's a follow-up paper in 2006. Yes. We haven't really planned this yet, but we were talking about making it spherically, well, not symmetric, but using a spherical, configuration. We call it grid. Maybe using a logarithmic grid because we're more interested in the dense parts in the center. But this is something that I haven't really, I have no exact plans yet. It would have been nice to have them so I could have presented them to you and asked for, guidance. But it's still, just a dream. Yeah. But that's what I'm planning to do.
I would like to ask that in this study that maybe done someday, that doesn't matter which is the mechanics why the cloud collapses.
No, we thought we'd let you do that. Because you're interested in that, so maybe these could be combined later on.
It's cooling, right? Collapse because of cooling or not? Or what?
It's just,
Is that gravity? Is that cold?
Just some compression, turbulent compression.
That's okay. For 3 reasons.
You can go through all the reasons for starvation and make them cloud cool.
but that's it. There are some references.
Questions, comments?
Everybody's still shocked by
Yeah.
the discovery that there are inconsistencies depending on how you distribute.
Yeah.
I mean, if it's true, it's kind of
I mean, one thing that one could think of here is that the certain calculations of averages are incorrect, or possibly also work incorrect.
Well, in fact, until 2 days ago.
And which one? Oh, that one?
For instance.
The one which you fixed, you mean?
Yeah,
Yeah, but that was-
that's not what we were seeing.
No, that's
No, that's not what but
I think
I guess it still proves
yeah,
the
something
point.
of that sort, yeah, because
But I mean, if it decreases, whatever you do, if it has any possibility, and otherwise they would have complained much before that. Then if in one case it decreases, and in the other case it does not. That's weird.
I think we should sit down
Mm.
and get ready to show.
that would be great, yes.
Did you try to run the normal viscosity or taking over?
No, no idea. So we're done with hyperviscosity.
Dangerous hyper, it may be sensitive to conservation, probably not, right?
Do you find that your initial conditions make a difference?
Well, they think that was probably one of my comments, that they were different, of course. Once, if you first use a different layout of processes, the initial condition is different each time.
Why is it different? Yeah, because
So
of random noise, but that shouldn't be it.
I mean,
No,
It's-
but
it's an
it's
ability.
random noise, I think. What was the initial condition here? It's not random noise.
Gaussian noise.
Hmm?
Gaussian noise.
Yeah. Mhm.
but I mean, unless you are very close to the threshold where the whole thing happens, I wouldn't expect that to make a difference. So it's true in that sense. It's not exactly the same calculation, but if the problem, if the correct solution is so dependent on the initial condition, then that certainly needs more investigation.
So our chairman and we have to talk to our systems guy in 8 minutes, and so that for our chairman from the Commission Committee is chairing the afternoon session again with the decision.
So let's thank Anne again.